The simulation hypothesis suggests that our reality, including the physical universe and everything in it, may be an artificial simulation similar to a highly advanced computer program. This intriguing idea suggests that a sufficiently advanced civilization can create realistic simulations of its predecessors or of completely different worlds, leading to the possibility that we are currently living in one such simulation. This concept has become widespread in popular culture and philosophical discourse, especially in light of rapid advances in technology and virtual reality. One of the key arguments in favor of the simulation hypothesis is based on the idea of probability. If advanced civilizations are capable of creating multiple simulations, then the number of simulated realities may far exceed the original base reality. This implies that the beings in these simulations are vastly outnumbered by the beings in the original universe. Consequently, the probability that we are in the original reality is becoming less and less likely, leading to the conclusion that we may indeed be part of a simulation. This hypothesis can also be related to the concept of multiple universes. If our universe is just one of many simulations created by advanced beings, then this implies a vast multiverse in which there are countless variants of realities. Each simulation may have different physical laws, cultural histories, or even evolutionary paths, resulting in multiple possible universes different from our own. In this context, the term multiverse goes beyond traditional interpretations in cosmology, where multiple universes arise from various cosmological events, to include universes created by intelligent design. Exploring the simulation hypothesis encourages us to rethink fundamental questions about existence, consciousness, and reality. If our understanding of physics and the universe is only part of a deeper simulation, this raises questions about the underlying purpose of these simulated realities and the nature of the beings who create them. Scientists, philosophers, and technologists are delving into this fascinating topic. The simulation hypothesis serves as a bridge between advanced technology, theoretical physics, and thinking about our place in the wider universe, illustrating how interconnected these concepts can be. The concept that our universe may be a simulation within a larger reality invites us to consider the possibilities of existence beyond our immediate perception. If we live in a simulation, it implies that there is an underlying reality, a more fundamental level of existence created or controlled by advanced intelligences that are potentially beyond our comprehension. This idea suggests that everything we perceive, from the laws of physics to our consciousness, may be the product of an elaborate program designed to reproduce or learn a particular aspect of reality. One intriguing aspect of this concept is the idea that there are interconnected layers, where each layer may represent a different simulation or level of reality. An advanced civilization capable of creating such simulations could harness vast computing resources, creating an environment in which every detail, from subatomic interactions to cosmic evolution, is programmed. As technology advances, our own advances in virtual reality and artificial intelligence illustrate the plausibility of this concept, with increasingly complex simulations becoming indistinguishable from real experience for their inhabitants. In this case, the universe we live in may be a highly complex simulation designed for various purposes such as research, experimentation, entertainment, or even education. The inhabitants of this simulated universe, including all conscious beings, would be unaware of their existence within a larger structure. This can lead to questions about free will, consciousness, and the fundamental nature of existence itself. If we are indeed living in such a simulated reality, it raises profound questions about the Creator's intentions and the parameters set for our simulated world. Moreover, multiple simulations can coexist within this broader reality, resulting in a range of different experiences and physical laws. Each simulation can be created according to its own rules, offering a rich tapestry of realities that encompasses not only our universe, but countless others, each with its own unique characteristics. This harmonizes with the concept of a multiverse in which different universes arise due to changing conditions or history. Taken together, these considerations show that viewing our universe as a simulation within a larger reality challenges our notions of existence and forces us to consider the underlying nature of everything we observe. The possibility of simulated universes entails many philosophical and scientific implications that challenge our understanding of reality, existence, and consciousness. From a philosophical perspective, one important question is the nature of existence itself. If our universe is a simulation, it begs the question of what reality is. Are experiences, feelings, and thoughts less valuable when they occur in a real-world context? This research pushes the boundaries of traditional metaphysics and asks us to rethink the nature of reality. The simulation hypothesis raises profound debates about freedom and determinism. If our lives are governed by predetermined algorithms created by an external planner, do we really have control over our decisions? Furthermore, if we have control, how do we access the parameters of the simulation? This dilemma raises debates about moral responsibility because concepts of right and wrong can take on different meanings in a simulated context where outcomes can be manipulated or observed. Scientifically, if the simulation hypothesis proves true, it will challenge the foundations of physics and cosmology. The theories that define our understanding of the universe, including quantum mechanics and relativity theory, can be seen as mere rules within a larger overarching system of simulation. Scientists must develop new methodologies to study the underlying code or principles that govern this simulated environment. This could lead to the development of new scientific paradigms that explore the intersections of technology, consciousness, and fundamental cosmic laws. In addition, the existence of simulated worlds raises questions about the nature of memory. If conscious experience occurs in a simulation, questions arise about the source of memory. Are simulations really intuitive, or are they complex, common-sense constructs? These reflections may challenge our understanding of artificial intelligence and the role of intelligent machines, as well as impact the ongoing ethical debate about artificial intelligence and robotics. When we think about concepts of real things, the conversation becomes interdisciplinary, bringing together philosophy, science, technology, and ethics. By exploring these topics, we form a deeper understanding of our place in the cosmos, questioning the very nature of reality, existence, and what it means to be truly alive in a potentially simulated universe. Figuring out whether our universe is a simulation is not an easy task, but intriguing ideas are emerging in philosophical and scientific discussions. One compelling approach is to look for signs of computational limitations in the fabric of the universe. Proponents of the simulation hypothesis suggest that, like digital simulations, our universe may exhibit discontinuities or anomalies that indicate that it is not a perfectly continuous reality. For example, studying physical phenomena that appear quantized, such as discrete values of energy levels in atoms, can hint at hidden pixels or resolution limits of a simulated cosmos. Another avenue of inquiry might be to look for inconsistencies or mathematical patterns that are more consistent with programming or computational shortcuts than natural processes. If our universe operates according to certain rules that resemble coding principles, researchers may find evidence of such structures through precise measurements in particle physics or cosmology. For example, inconsistencies in the behavior of fundamental particles or unexpected correlations in the cosmic microwave background radiation can serve as signals indicating a simulational nature. In addition, advances in technology, particularly quantum computing and artificial intelligence, may facilitate the exploration of whether we exist within a simulation. By developing more sophisticated algorithms and simulations, scientists can draw parallels or notice limitations in their own creations that reflect features of our universe. This could provide insight into how a more advanced civilization might construct a simulation, and therefore how we might determine if our own universe follows similar patterns. Finally, philosophical and theoretical frameworks may open the way to the discovery of a simulated universe. Questions about consciousness and observation can lead to deeper discussions about the nature of reality. If consciousness plays a role in shaping what we observe, and this idea is supported by the interpretation of quantum mechanics, then the possibility arises that our perception may be influenced by the boundaries of the simulation. Thus, reassessing how we perceive reality and questioning the nature of our observations may also contribute to the debate about whether we are inhabitants of a simulated existence. Overall, while the discovery of a simulated universe may be elusive, an interdisciplinary exploration of these ideas, combining ideas from physics, technology, and philosophy, can enrich our understanding of reality and inspire innovative research that may one day shed light on the nature of our existence. The idea of creating a simulated world raises some ethical questions about basic morality, responsibility, and what it means to live this way. One of the biggest challenges is communicating with real people in this simulated environment. If we create intelligent life in a simulation, we must consider the moral implications of its experiences and rights. Do these people have the same thoughts as living beings in the real world? Does their pain, happiness, or independence matter if it is merely the result of a simulation? These questions make us think about the knowledge and responsibility we have towards people like us. Moreover, the possibility of playing with electrical impulses becomes an important ethical issue. Creating a comparative world leads to an imbalance of power and authority. Those who design and control the simulation may have the ability to shape reality to their liking, which can pose a risk of power. This phenomenon deals with moral issues in our world related to social structures, oppression, and oppression. The responsibility of creators will go beyond mere design to include the ethical management of simulated creatures and the environments they inhabit. In addition, modeling different scenarios, cultures, or social structures raises ethical dilemmas related to experimentation and observation. If the creator runs scenarios that entail painful or traumatic experiences for the inhabitants, what moral justification can be offered for such actions? This becomes more complex when one considers the possibility of suffering in simulations. Would it be ethically acceptable to simulate historical atrocities or societal collapse as a means of study or entertainment? Such activities may desensitize creators and observers to real-world problems, throwing them into complacency about real-life ethical considerations. Finally, the distinction between creator and creation raises philosophical questions about identity and existence. Reducing the nature of reality to a simulation construct blurs the boundaries between the creator and the beings created by his design. Can creators be considered gods? And if so, what ethical principles should they adhere to? These reflections prompt deeper introspection and prompt the creation of an ethical framework that would guide our behavior if we were given the power and opportunity to create meaningful simulated worlds. As a result of these reflections, our approach to simulations should be one of responsibility, compassion, and respect for consciousness, echoing the ethical principles that should govern our interactions in the real world. String theory fundamentally changes our view of the universe by positing that the smallest building blocks of matter are not point particles, but one-dimensional objects known as strings. These strings can vibrate at different frequencies, and different modes of vibration correspond to different particles, effectively unifying the forces and constituents of the universe. One of the most exciting aspects of string theory is its proposal for additional dimensions beyond the four we normally experience. 3 dimensions of space and 1 of time. In string theory, additional spatial dimensions are needed for mathematical consistency and to account for all the vibrations that strings can exhibit. Although we are familiar with the 3 dimensions of space, length, width, and height, string theory suggests that there are 6 or 7 more dimensions that are compacted or convolved in such a way that they remain hidden from direct observation. These extra dimensions may be so small as a fraction of the size of subatomic particles, that they are extremely difficult to detect with current technology. The concept of compacted dimensions offers intriguing implications for fundamental forces in our universe. For example, how these extra dimensions are formed and configured can affect the types of particles that arise from string vibrations and determine the strength and behavior of fundamental forces such as gravity and electromagnetism. Different configurations of these extra dimensions can lead to different physical phenomena, potentially explaining some of the observed inconsistencies in particle physics and cosmological observations. Moreover, the existence of these additional dimensions points to a richer and more complex cosmos. If there are indeed more dimensions, they may play a role affecting other theoretical constructs such as black holes and the very fabric of space-time itself. In some advanced interpretations of string theory, the dynamics of these hidden dimensions may shed light on cosmological questions, including the nature of dark matter and dark energy. While physicists continue to explore the implications of string theory and its extra dimensions, the prospect of a multidimensional universe offers not only a deeper understanding of fundamental aspects of reality, but also exciting ways to bring together the various forces of nature. These ideas open new avenues for research, suggesting a re-evaluation of everything we think we know about the universe and challenging our ideas about what comprises reality. The Kaluza-Klein theory is a novel theoretical scheme that combines the principles of general relativity and electromagnetism, introducing additional dimensions beyond the familiar 3 spatial and 1 temporal. Developed in the early 20th century by mathematician Theodor Kaluza and later refined by physicist Oscar Klein, the theory originally sought to unify gravity and electromagnetism into a unified whole. The essence of the Kaluza-Klein theory is that through the inclusion of a 5th dimension, all the complexities of electromagnetism can be mathematically represented as a geometric property of space-time. In the Kaluza-Klein formulation, the 5th dimension is compacted, that is, rolled up into a small circle, and therefore not directly observable in our everyday experience. This densification allows additional physical phenomena to exist without disturbing the 4-dimensional fabric of space-time we perceive. The extra dimension fundamentally changes the equations of motion of particles, leading to the emergence of electromagnetic interactions as a natural extension of gravitational theory. The implications of the Kaluza-Klein theory extend to the field of higher dimensional physics and the consideration of multiple universes. By introducing the concept that our universe functions within a higher dimension, it naturally invites thoughts of parallel or alternate universes. In some versions of Kaluza-Klein theory, different compactification schemes can lead to different physical laws. This could mean the existence of multiple universes, each characterized by different properties, forces, or types of particles shaped by the geometrical structure of these extra dimensions. Moreover, the extra dimensions offered by Kaluza-Klein theory may affect our understanding of fundamental forces. In the broader context of string theory, which also involves higher dimensions, these additional dimensions serve as vital components that help explain previously unexplained properties of particles and forces. This relationship not only emphasizes the importance of extra dimensions in modern physics, but it also forces researchers to consider cosmological scenarios in which different universes arise from different configurations of these dimensions. Overall, The Kaluza-Klein theory represents an important early attempt to unify gravity and other fundamental forces using higher dimensions, paving the way for further exploration of the nature of reality, the potential existence of multiple universes, and the relationships between the basic structures of our cosmos. As physicists continue to explore these ideas, the Kaluza-Klein theory remains a crucial stepping stone in the quest to better understand the complexity of the universe. The idea of the existence of objects or beings in higher dimensions opens up exciting possibilities for understanding reality beyond our normal experience. In everyday life, we perceive a three-dimensional world characterized by length, width, and height, and one dimension, time. However, if additional spatial dimensions do exist, as theories such as string theory and Kaluza-Klein theory suggest, then beings or entities occupying these dimensions will have fundamentally different experiences and perceptions of reality. Beings in higher dimensions may possess qualities that exceed our ability to comprehend. For example, while we can only move freely in three spatial dimensions, a being existing in a higher dimensional space could move in ways that seem impossible to us. They may have the ability to pass through objects or perceive spatial relationships that remain hidden to us. This concept often leads to the analogy that it is difficult for a two-dimensional being to understand all the qualities of three-dimensional objects. For example, a flat being in a two-dimensional plane will perceive only the edge of a solid sphere as a circle, completely missing its volume and depth. Similarly, beings in higher dimensions could sense the complex structures and interconnections of our universe in ways we cannot imagine. If higher dimensional beings interacted with our three-dimensional world, their perception could encompass multiple perspectives simultaneously. They may see our universe as a slice or projection of a more complex reality, capable of observing all possible configurations of particles and forces. Their ability to access and manipulate a wider range of dimensions may give them insight into the very fabric of space-time that remains elusive to us. Such beings may also experience time differently, potentially perceiving it as a more dimensional construct rather than a linear progression, leading to a radically different understanding of causality and existence. The implications of their existence challenge our ideas about consciousness and the nature of life. If beings from higher dimensions interact with our world, what kind of consciousness do they have? Will they realize their size or see their lonely reality? These reflections are related to philosophical questions about psychology and life, and encourage us to expand our understanding of the meaning of life and consciousness in a multifaceted context. By thinking about higher things, we enter a world beyond philosophy and science. Exploring these concepts is more than just putting up with knowledge. This invigorates our quest to unravel the complexities of the universe and our place in it, inviting an ongoing dialogue and exploration of the very nature of reality. The search for experimental evidence for the existence of higher dimensions is a complex and ongoing challenge for theoretical physics. Although direct evidence remains elusive, several experimental approaches and observations provide tantalizing hints that higher dimensions may play a role in our understanding of the universe. One well-known method involves particle physics, particularly large particle gas pedals, such as the Large Hadron Collider. In the context of string theory and other higher dimensional structures, we can expect the potential discovery of particles or interactions that only arise from extra dimensions. For example, if extra dimensions exist, they could affect the behavior of fundamental particles at energy extremes, possibly leading to specific features in collisions. Researchers are particularly focused on finding evidence for the existence of mini black holes, or particles, which could hint at the underlying structure of higher dimensions as they involve particles at unprecedented energy levels. Another approach utilizes gravitational waves, which are ripples in spacetime caused by massive astrophysical events, such as black hole collisions. The detection of these waves by observatories such as LIGO and Virgo opens up the possibility of studying gravitational interactions, which may reveal deviations from our current understanding based on the general theory of relativity. If unexpected patterns or anomalies are observed in gravitational wave signals, this may indicate the influence of extra dimensions. Cosmic observations also provide insight into the possible existence of higher dimensions. For example, the nature of dark matter and dark energy, the invisible forces that seem to dominate the universe, may be influenced by extra dimensions. Some models suggest that the interaction between ordinary and dark matter can be explained differently by involving additional dimensions. By investigating the distribution and behavior of dark matter in galaxies, scientists seek to distinguish between standard physics and scenarios involving higher dimensional theories. Finally, the study of cosmic inflation, the rapid expansion of the universe immediately after the Big Bang, raises questions about the mechanisms underlying this phenomenon. Theories that account for higher dimensions may provide alternative explanations for inflationary dynamics, potentially providing signals in the cosmic microwave background radiation. Such signals may provide indirect evidence for the existence of dimensions beyond the four we normally perceive. Although reliable experimental evidence for the existence of higher dimensions has yet to be obtained, these lines of research reflect the growing interest in unlocking the mysteries of the universe. As technology improves and our understanding deepens, the search for elusive signs of higher dimensions will undoubtedly continue, advancing our efforts to comprehend the fuller scale of reality. The concept of higher dimensions offers fascinating insights into phenomena that challenge our understanding of the universe, particularly dark matter and dark energy. Traditionally, we perceive our reality through three spatial dimensions, but theories such as string theory suggest the existence of additional dimensions that we cannot easily observe. These additional dimensions may provide an alternative to traditional explanations of dark matter and dark energy, suggesting that the forces and particles we observe are only part of a more intricate and multi-layered reality. One intriguing idea is that dark matter may be connected to these higher dimensions in a way that interacts with our familiar three-dimensional world. Rather than being composed of unknown particles, dark matter may be a manifestation of gravitational effects from matter in another dimension. This means that the gravitational attraction we associate with dark matter is the result of the influence of these invisible spheres. Such a concept could simplify our understanding of why galaxies spin at such high speeds, as gravitational effects from the extra dimensions could explain the observed discrepancies. The dark energy responsible for the accelerating expansion of the universe may also be influenced by higher dimensional theories. If the universe has extra spatial dimensions, then the energy that is pushing the cosmos apart may come from the interaction between these dimensions. Rather than being a mysterious force operating exclusively in our three-dimensional space, dark energy may be a natural result of the geometry and dynamics of the higher dimensional universe. This suggests a connection between the expansion of the universe and the structure of space-time itself, beyond our normal understanding. Studying these higher dimensions not only enriches our theories of dark matter and dark energy, but also opens the door to many possible discoveries. The interactions between these elements reveal connections between forces that we today consider separate. As physicists continue to unravel the mysteries surrounding these phenomena, our conceptual structure of reality may become more sophisticated, revealing a world far more complex and interconnected than we thought.